Continuing with our discussion on the general purpose registers of 8085, today we'll be looking at the program counter. So program counter is a 16-bit accessible register of 8085. Fine. It's one of the most important registries and it helps us in keeping track of the memory. It sets the sequence of the program and helps us in keeping track of the program memory. As the name itself signifies, it is a counter that actually keeps track of the program. So where it basically keeps track of the address from where we are actually going to execute uh, the start of the in certain program that we are going to be executing. It will basically carry the starting address of that very program and helps us in keeping track of that program. Fine. It basically holds the address. PC holds the address. Uh, it basically holds the starting address. Holds the starting address, which puts the T1 state, that is the first execution state. The program counter will basically uh, will actually mark the address, the starting address from where the execution of the program will basically begin, and that address will be uh, put on the address bus for the memory to be so that the 8085 basically can fetch the memory location using that address. So this basically takes place in the T1 state. In the T2 state, that's the next cycle that we'll be discussing later on. PC is basically incremented by 1. So once it basically holds the starting address, we need to keep that stored. So in the next state, PC will be incremented by 1 so that in the next once the next execution cycle begins, PC will at the next location now the address will be stored. It will not override the previously stored address that was done in the T1 state. Fine. So in T1 state, PC fetch the address from where the basically the execution of the program has to begin. It basically will hold that starting address uh, through the fetching it through the address bus of the 8085. Keep it on hold. Fine. So in the T2 state, PC will now be incremented by 1. So PC is a register of its own. Fine. So it basically has a number of. So in this register, you can keep on incrementing it every time. So every time a new instruction cycle begins, the PC is basically incremented every time in its T2 state so that the previously stored address does not get overwritten, and this way a sequence or of the program memory will be uh, a sequence will be set as well as the program memory will be kept track of. Fine. So basically it helps us in execution of the program and storing the address from where we have started the execution of the program, and in every instruction cycle it will be incremented by 1. By the end of every machine cycle, the PC will hold the address of the next location from where it basically has to fetch the next instruction. Fine. So by the end of one machine cycle, PC will hold location of uh, mm, PC will hold address of next PC will hold the execution of hold the address of the next location in program memory from where a byte is fetched. Fine. So say for example this is our PC program counter. Fine. So PC is and this is your first memory location. So for example 0000 of the PC, and since it's a 16-bit register, so in this register it will store the memory location of from which we have to basically start the execution of the program. Fine. And that happens in the T1 state of a machine cycle. Fine. There are instruction cycles and there are machine cycles. We have, as already defined, machine cycles will consist of number of T states. So in a machine cycle there can be a number of T states, T1, T2, T3, T4. Say for example it's an opcode fetch machine cycle or a memory read machine cycle that we have discussed. So in the T1 state, PC will be basically read so that we can actually uh, mark the mark the location from where the execution of the instruction has to take place. And in the next machine cycle, and in the next T2 state, what will happen is that PC will be incremented by 1. So use by this, what happens is that PC already basically has uh, in the T1 state, PC will basically uh, forward this address to the address bus. Fine. AD7 to AD0 to AD15. Fine. So it's a 16-bit register. Address bus is also 16-bit register. So PC in the previous machine cycle, PC was already incremented in the T2 state, and it is already pointing to a location on the program counter from where it has to start the execution of the instruction. So one now this memory location is already stored in the PC. So we need to know, the microprocessor needs to know this memory location, needs to know this address. So where from will it get this address? It will get it from the program counter. So program counter basically uh, feeds the memory location, feeds the address of the memory location from where the instruction is basically written onto the address bus so that it is forwarded to the microprocessor for further processing. And in the T2 state, the program counter is already incremented by 1, and so that it already points to the next location from where the once this machine cycle is over, there will be another machine cycle. So once the next machine cycle will start, program counter will again feed the address bus. So at this time it will already be knowing the memory, it will already be having the information of the next location of the memory from where the next uh, data or instruction has to be taken. Fine. So it can be any type of machine cycle. It can be an opcode fetch machine cycle, a memory read machine cycle. So program counter basically helps us keep track of the memory, and so that the so that the program can be executed in a timely manner. And all these addresses are basically uh, the location of the addresses are basically stored in the program counter, and this is why program counter is important for execution of the instructions. Fine. So it's a 16-bit accessible register. It keeps track of the program memory and helps us set the sequence of the program. Fine. The memory location already basically has the data that needs to be processed. The first memory location may be an instruction. The second memory location may be referring to a data. Third memory location may be referring to another instruction. So that address locations need to be fed to the microprocessor, and this is done through the program counter. Not only does it feed it, but it also keeps track of that memory location and keeps it in store. So the sequencing of the program is done by the program counter and also keeps track of the memory location. So this increment that we actually are talking about here in the T2 state, the program counter is incremented by 1. This is done by the ALR, increment ALR or decrement ALR, that we have already discussed in the as one of the registries of the 8085. So it's an inaccessible register. The function of ALR is to only help increment the program counter by 1 in every T2 state of every machine cycle. So once we'll start with the instructions and also with the programming, these things will become more and more clear. The program counter keeps track of the address of the instruction that is being executed. It keeps track of the address, not the instruction itself. So next is stack pointer. So stack pointer is just another general purpose register. It's again a 16-bit accessible register of the microprocessor, and it also holds the addresses. Just like the program counter, the stack pointer also holds the addresses to keep track of the, it does not keep track of the program memory, it keeps track of the stack memory. And this is done for implementation of modular programming. So what's a stack memory? First of all, we actually have uh, three types of memory. We'll be having we have the program memory. So program memory basically is that part of the memory that's meant for programs, for execution and writing of the programs. You have the data memory that is meant for storing data. And you have the stack memory. So these are the three memories that are associated with the 8085 internally. So it is part of the main memory. That is set aside by the programmer for use in a particular fashion. So it's basically set aside by the programmer himself for used in a particular fashion, basically used for modular programming. So what we do in case of modular programming is basically the problem is that which is actually under consideration is divided into a number of small independent modules that are coordinating with each other, and these modules are divided on the basis of the functionality. So the concept basically here is that it helps us in addressing problems associated with basically lengthy and complex programs, like in case of debugging. We, so there, this memory block is used. Fine. So it basically works on the divide and rule policy. So what basically happens here is, say for example, uh, we are performing a certain program, we are executing a program here, and there is a certain other program that needs to be executed within this program. So before this program can be executed, uh, the the location of the last known instruction or that was being executed in this particular program needs to be stored, and that is stored by using uh, various instructions in the microprocessor that we have, like push and pop. So basically push helps us in mm, there are two instructions, push and pop. Push helps us in So push basically helps us in saving the contents of any register pair on the top of the on the stack memory, or and pop will basically helps us in retrieving that memory location. So a particular program will have a certain routine and it will have a subroutine that needs to be executed. And that, say for example, you are using the instruction call. You are uh, you are running a program, but within that program you have to basically refer to some other program uh, that has been already defined somewhere else at some other location. So you need to basically at that memory location, first of all call that other memory location where that particular instruction has been written. Right? There are certain programs within the program you'll have another program written, and that program needs to be executed. So that can be executed by calling that particular instruction. So before we go to this instruction, we need to save the address of this particular location, so that once this sub instruction is basically executed, after that we need to go back to the original location. So where to save this address? This address is basically stored on the stack memory, and stack memory is basically stored uh, up down. That means first, uh, stack memory is stored up down. That means first, the top of the stack will be this address will be stored on the top of the stack, and then the next address will be stored below it, and so on and so forth. So this way we can basically execute a subroutine, a sub program within the program, using the help of a stack pointer and stack memory. And there will be certain instructions that will be associated with this. You have the call instruction, you have the push instruction, the pop instruction. So different instructions will be used for accessing the uh, stack register. Fine. And this stack memory is filled up down, or you can say last in first out basis. Uh, that is, the last will be filled, last will be in, and it will be first to be retrieved back. Right? The last memory location of the stack memory will be the last to be filled in, will be the first to be taken out when retrieved. So stack pointer and stack memory help us in execution of subroutines or subprograms within the program, and it helps us in keeping the track of the address where the memory location needs to return back to once the execution of the subroutine or the subprogram has been carried out. So stack memory is basically where you will store that uh, subroute, where you will store the location of that address where the program needs to be addressed, and the stack pointer will basically indicate to that location of the last item put onto the stack. Fine. So when you put basically something onto the stack, push will be used, and when you basically take something out of the stack, pop instruction will basically be used. Fine. So every time, stack pointer basically points to the location on the stack memories, and stack memory is basically used for execution of subroutines or even interrupts in that for that matter. So this is about program counter and stack pointer, and both are 16-bit registers, both are accessible registers, and they are both important. Program counter points and keeps track of the program memory. Stack pointer points and keeps track of the stack memory. Program memory is basically where you will execute your program, while a stack memory is where you will be basically holding the address of the uh, actual program instruction before calling on to the subroutine. So this way, the stack pointer basically keeps helps us in since if you do not store this address onto the stack memory, uh, the these locations will be basically overwritten. So stack pointer basically helps us in retrieving back that location from where the original instruction needs to be executed. So next is instruction register. We'll do this in the next session.